Okay, good afternoon, everyone. Welcome to the sixth session of our GIS online course. Today, we are honored to have with us a distinguished speaker, Professor Ming-Der Yang, the Dean of the College of Engineering at National Zhongxin University. Professor Yang will be sharing with us a cutting-edge topic on the AI remote sensing in smart agriculture and the sustainable environment. So in recent years, Taiwan has witnessed the rise of the smart agriculture, where the adoption of high-tech solution of agricultural decision-making has become a trend. Professor Yang's research area include the disaster prevention engineering and the geographic information system and the remote sensing image processing. So he has recently developed a air-ground cooperation for optimal rice harvesting model by using the UAV and the mobile device. Through the big data and the AI algorithm, he has successfully trained a model for optimal rice harvesting, integrating weather information to estimate the future moisture change, and providing a virtualized harvest decision-making service on a cloud platform. So this will assist the user in making the precise judgment on the optimal harvest timing. So we believe that in this session, Professor Yang will showing with us the potential impacts and the influence of AI on people's future life. So let's look forward to this exciting lecture together. So Professor Yang, please.
Yeah, thank you for introduction. My name is Ming-Der Yang. I'm very good to share these 2 hours about AI remote sensing in smart agriculture and sustainable environment. My name is Ming-Der Yang. Yeah, I mentioned before. I'm a distinguished professor and serves as a dean of a College of Engineering. I'm also in Department of Civil Engineering in National Zhongxin University. I also host a unmanned vehicle research center for autonomous driving or flying, especially use AI, artificial intelligence technologies. Here is some of my resume. I was a picture. I got my bachelor degree in civil engineering from National Jiao-Tong University, and then I got my master and PhD degree from civil and environmental engineering and geodetic science in Ohio State University in America. Recently, I put a great effort on using UAV to monitor environment and agriculture. So I got my accredited from National Science and Technology Council as an outstanding research award. Also, technical breakthrough awards in 2020, 2019, and even in last year, 2020, 2022. Also, this breakthrough was accredited from MediaTek as a special prize. MediaTek is a semiconductor design company. I think it's one of the biggest company in the world. So I gonna give a brief introduction about remote sensing, and in the second half, I will describe AI, artificial intelligence, and applications. What is remote sensing? Remote sensing is a technology of obtaining information about objects through the analysis of data collected spatial instruments that are not in physical contact with the object investigation. That means we do not touch the object, and we can detect what the object is, or what size the object, or what the object composite of, or the object moving or trace the object. So remote sensing is the science and art of obtaining information. We should get those information by employing some remote sensors. For example, your eyes as acting as a sensors we use the most in most time, that responds to the light reflected from the object. So collect data is the first step in remote sensing. The second step is to analyze those data. So how to process those data is very important in remote sensing, especially image processing. So two major components in remote sensing are data collection and data analysis. So in the first session, I'm gonna focus on how to collect data and why we can use the data to analyze the interested objects. In many respects, remote sensing can be thought of as a reading process and using various sensors and to collect the data. It's the opposite side of in situ sensing or on-site observation. You may be familiar with this thermal sensors during the period of COVID-19. Every time when you enter a building, you have to be sensed what is your body temperature. So it's the typical remote sensors to detect your body temperature. And because the temperature is radiation, so the sensor doesn't need to contact with you. So it make it convenient to detect all visitors or pedestrians on the street. Here is a brief of history of remote sensing. At the first, scientists tried to use a balloon to fly in the sky and take a photo. So back to 1958, the first person to take area photos is using a balloon. And his goal was to make land surveys from area photography. So this is the very first try of remote sensing. Then In 1907, a German developed the skill of area photography. They use a pageant carried camera to take an area photo. Then Wright brothers took a videographer from Sweden to take the first aerial photo from an airplane. So it's the first time people take on the airplane to do photogrammetry. After half a century, we enter into a new age. It's a so-called satellite age. Since the project Apollo launched, it's a mission to the moon. They need a map for the lunar surface, especially for the proposed landing site. So we should make a map of the moon surface for the preparation of the project Apollo. The image from the Apollo 9 is a multispectral full-length camera that they were digitized and used to develop technology for processing data, Landsat data. At that time, they use the analog data, so that why we need to digitize all of the photo. But right now we use digital camera or digital sensors. So this step has been removed. In 1972, civilian satellite remote sensing has been developed. On July 1972, the first civilian satellite designed to image Earth land surface was launched. On board, the satellite originally named Earth Resource Technology Satellite, but later on, it was renamed as a Landsat 1. Right now, we have a Landsat 2, 3, 4, 5, 6, 7, and 9. Landsat 9 was successfully launched on September 27th, 2021. It's NASA and USGS cooperate to process the project. The Landsat program provides the longest continuous space-based record of the Earth's land. Landsat data give us information, especially for making informed decision about Earth resources and the environment. So if you are interested about the Landsat, you can visit the Landsat.gsfc.nasa.gov. You can take a look at about the whole series of Landsat satellites. So from 1858, we use a balloon. To the recent decade, we use a spatial station or satellite image. It's a very big improvement in remote sensing. And we have 42,000 satellites in the sky, so it's kind of crowded. And right now, there are several companies try to launch more and more satellites, especially low orbit. So this figure shows us the satellite remote sensing of the satellite system. We have a sensor on the ground. We have a airplane. We have a drones. We have a commercial aircraft and helicopter, and also balloon. A month ago, they were several balloon flew to the sky of North America. So that caused a very big issue in international international problem. And beyond that, we have different satellite, and those satellites can be used as the data resources for remote sensing. So on the ground, we have a UAV. We have a CCTV camera, and in the low ground, we have a UAV drone and LiDAR optical sensors. And little bit higher, we have area photography, and little bit higher, we have airborne multi or hyperspectrum sensors. And in space, we have a space shuttle. We have satellites equipped with multi-spectral sensors or hyperspectral sensors or SAR. Why the remote sensing data can be used to detect the objects far away? Because every object has a different electromagnetic wave. The vibration of the particles and change in the energy level of matter produce a electromagnetic wave of a different frequency. So frequency is a very unique characteristic for every object. Electromagnetic waves are the main target for remote sensing of energy. Sensors can detect reflected or radiated electromagnetic waves from object to determine the category, specific physical state, or feature of the substance, either on the earth or even underwater. Electromagnetic waves interact with substance in the atmosphere, causing interference such as scattering, absorption, and radiation. That means before we make use of those remote sensing data, we should do some atmospheric field correction because the scattering effect cause some inaccurate signal that we should do some radiometric correction first. So as I mentioned, the frequency is the most important character of the objects. And as we know, the electromagnetic wave has a constant speed, which is the light speed. So if a speed of light equal to lambda is a wavelength plus frequency, and c the light speed is constant, so that the wavelength and the frequency are opposite correlated. And the other thing we should know is the energy of the wave is equal to h. It's a constant, so-called Planck constant, plus c divided by lambda. So energy is proportional to the inverse of the lambda. In summary, the higher the frequency, the shorter the wavelength, and the greater the energy. And every object has a different reflectance in different wavelengths. So we can use this spectral characteristic, just like a fingerprint, to identify what kind of object we are observing. This is the frequency line. As the human eye can only receive a very narrow band. As I mark here is a visible band. Most of the bandwidth people eyes cannot receive. So we design a lot of different sensors to receive those radiation in different frequency or different wavelengths. Then we can analyze those data from low to high frequency. The main types of electromagnetic wave include the radio wave. You can see in your left-hand side, you have a radio wave. Then we have microwaves. Then we have infrared radiation. Then visible light and ultraviolet radiations, so-called UV. Then X-rays and gamma rays. So X-rays and gamma rays have a very strong energy, so that if people contact those rays, it could cause some abnormal change for your body. The range of the electromagnetic waves, the human eye only can detect is so-called visible light, which has a wavelength between 380 and 780 nanometer. From the 780 meter is a ray length, and 380 meters is a purple. So so a bit outside this visible band, outside the red, we call the infrared. Outside the purple light, we call ultraviolet. In remote sensing area, we focus on one phenomena of the object responding to the light. When the light hits the object, it could scatter, it could reflect, it could absorb, and it could penetrate. And what we focus on is a reflection from the objects. And when the Earth receives the solar radiation, it can observe and reflect those energy. So as we can see, in invisible band is we have a high spectral irradiation. So we designed different sensors on board on satellites to record those reflectance from 0.1 nanometer to 100 nanometer. We use this as a resource satellites. Then I'm sorry. We use this area to record X-rays and ultraviolet. And for the about the visible light from the 0.4 to 0.7 nanometer, 0.4 to 0.7 micrometer, so-called micron. It's a visible band, and little bit longer wavelengths we record as a near infrared and thermal band. And this area we use as a Earth resources satellites image. And a lot longer wavelength we have infrared spectrum. It's to detect atmospheric gases. And for the very long wavelengths, like a meter, 100 meters, it's a radio wave, so that we use it to transit the signal. And this is this figure provided by NASA to illustrate the thermal distribution over the Earth for December, for March, for April. So, in summary, if we use the electronic magnetic wave, different frequency respond to different object and object size, and even different composition of substance. For example, in here is a very a typical spectral figure. In different wavelengths, substance has have a unique reflectance. We can show it from this reflectance curve. The same substance may have a different reflectance curve under different physical condition. These features of the reflectance curve can be used to identify land use land cover types or estimate their physical properties. Like this figure, the dashed line is the water reflectance. As we know, water can reflect most in between blue and green, so that you when you look at the ocean, it's look like green, and the water can absorb most of the red and infrared, so we can detect the water just by red or infrared image. And the solid line is vegetation reflectance. So we can see the on the left hand side there's a little peak. It's in green line, so that we can look at the tree and see the tree in green. It's because the green leaf reflect green light. On the other hand, the leaves reflect a lot of infrared, especially near infrared. So we use the infrared image to identify the health or the variant of leaves. And another dashed line is a dry bare soil line. The reflectance is a little bit higher and more constant in different wavelength compared to the other types of land type. So it's easy to identify the object of the soil on the earth from the sky. And if we mix soil and water together, that means a water body with high turbidity, and the reflectance will get higher. Or if in water or reservoir, the chlorophyll is high, so-called eutrophication, then the reflectance is high too, especially in near infrared. So it's make us easier to identify the water quality. If the water quality is good, the reflectance in near infrared is low. If the water quality is bad, especially eutrophic status, the reflectance is high. Even with the vegetation, we can detect which one is a coniferous tree or a deciduous, because the reflectance has a difference. As I mentioned before, most of the wavelengths we cannot receive from our raw eyes, so that we should design a sensor to receive near infrared or thermal infrared. But when we record those digital number, we should express in a figure to show the image. So we propose made of RGB, red, green, and blue. On the right-hand side is a false color image. It's composed of the near-infrared, red, green. On the right-hand side figures, near-infrared, which human eyes cannot detect, so we show it in red. So on the right-hand side, the red area is the high reflectance of near infrared, and red light represented by green, and green light represent by RGB, blue. So the color is different from the common sense. So let's call it a false color image. The false color image has been used a lot of in remote sense area, because most of the surface of the land was covered by vegetation. And you can see on the right-hand side, the dark area is water. As I mentioned early on, water absorb NIR, red light, and near infrared a lot, so it reflects very less, so it can be presented in very dark. And some area is a little bit light on the right-hand side, down lower right-hand side, because this area could be very turbid, with a very high concentration of soil in water, so that make the reflectance a little bit higher than other water body. Okay, in this part, I got some summary. The first one is remote sensing depends on the object's electromagnetic radiation, instead of physical contact for objects in investigation. So no contact with the object instead of how we tell if it's a remote sensing image or not. Remote sensing is a composite of two components, data collection and data analysis. Electromagnetic wave has a very specific phenomena. The higher the frequency, the shorter the wavelength, and the greater the energy. And the last one is a spectral reflectance is represents a reflectance curve of physical properties for every object. As long as you know the reflectance, the curve, or so-called spectral characters, then you can identify those objects with the remote sensing image without touching it. Okay. Then I try to introduce some satellite image system. The first one is the data collection methods. Two imaging methods include passive remote sensing and active remote sensing. So the passive remote sensing is to gather radiation that is emitted or reflected by the object or surrounding areas. Most of the time, the energy source is from the sun. When the sun deliver the energy to the object reflects it out, and satellite sensors receive it, record it, and transit it to the ground station. There are a lot of examples like photography, infrared charge couple devices, so-called CCD, charge couple device, CCD, and radiometers. And this is a major wave we use to observe Earth resources. The second method is active remote sensing. The sensors emit energy in order to scan objects in the area, which are the sensor can detect and measure some radiation that is reflected or backscatters from the target. That means the satellite emit energy to the objects. Then the object reflects to the energy back to the satellite. Then the satellite transits the information to the ground station. There are several examples like radar and lidar. So radar and lidar have a different wavelengths emitted from the sensors, so that make it as active remote sensing. And there are two satellite systems. Depends on it. Depend on their position to the Earth. The one is a geostationary satellite. This type of satellite has an orbit that makes at the same time to complete one revolution around the Earth as the Earth's rotation period. When observed from the Earth's surface, the position of the satellite relative to the Earth's surface remain constant at all time. So there's a circular geosynchronous orbit is 35,000 kilometers in altitude above the first Earth's equator. That means it always stay on a specific lane. It can always observe a specific lane. The second one is some synchronous satellite, which we use a lot for resources satellites to monitor the Earth. The orbit of the Sun synchronous satellite is characterized by an angle between the Sun and the satellite's orbit plane, which remains constant. Therefore, the satellite passes over the same geographic latitude and at the same local time. Most of Earth observation satellites are Sun synchronous satellites. This kind of Sun synchronous satellites has of orbit is about 800 kilometers from over the Earth's surface and give us Sun synchronous inclination of like about 99 degree. That means like formal sets, one of resource satellite, they pass Taiwan, Taichung, about in the morning 9:30, and every time when the satellite pass the Taichung will be at the same time. And there are two imaging methods. One is whisk balloon, and the other one is push balloon. Which whisk balloon is older method because they only have one camera, so they have to rotate to scan the all objects. The new one is a so-called push balloon. They just like this balloon, we have 100 and 1000 CCD equipped on the sensors, so they only have to move forward, then they can record everything on the Earth, so that we have more time to observe one pixel, so that the spatial resolution of each pixel can be higher and higher. Speaking of resolution, we have a 4 resolution capability, include spatial resolution, spectral resolution, radio resolution, and temporal resolution. Spatial resolution is we talk about most is so-called resolution. It represents the size of ground objects by each pixels corresponding to an image. So when we say the resolution is 1 meter, in general we mention a spatial resolution. There are 3 other resolution we should talk about is spectral resolution. As we mentioned earlier, every object has his spatial or specific spectral character, so that spectral resolution can help us to identify what kind of object it is, depends on the spectral image. The smallest wavelength interval can distinguish more detail. Well, we will talk about this later. The third one is radiometric resolution. That means the range of grayscale values used to quantify the energy of coming radiation from the Earth surface. That means how many bits you use to record 1 pixel. If you use more pixels, then you need more storage capacity, but you can distinguish very detailed reflection. The last one is temporal resolution. That means the time interval between image captured by the same area. As I mentioned, when the satellite passes over the sky over Taiwan at 9:30, then next time it will be visit the Taiwan at the same time. But when is the next time? Maybe 2 days later, or 1 week later, or 1 month later. The revisiting time is a so-called temporal resolution. Of course, it will be better if you can visit the same area every time, but usually it's kind of not economic. So for spatial resolution, it's an optical remote sensing system. The spatial resolution of a satellite refers to the size of the ground area. That's represented by 1 pixel at the satellite nadir point. The spatial resolution decreases as the viewing angle of the satellite increase. That means if the satellite has a satellite sensor has a certain angle, and the ground size will be larger. For example, the spatial resolution of a formal set panchromatic. So here, panchromatic means it's a black and white image, and usually panchromatic image has a better spatial resolution, but has less spectral resolution. And that means 2-meter resolution means each pixel represents a ground area of 2 meters. The spatial resolution of the multispectral image is 8 meters, means each pixel represents a ground area of 8 meters. So as I mentioned earlier, multispectral image has a low spatial resolution because it's 8 meters, but has a better spectral image because it could record blue, green, red, and infrared at the same time. So you can see, you can check the table down there. It's about the formal set has an altitude of 891 kilometers. It's a sun synchronous orbit, so it passes twice over the Taiwan Strait every day. But you can only take 1 image over the land because it's a passive satellite sensors. So during the nighttime, when the satellite passes over the Taiwan Strait, it cannot record the reflections of the Earth. But at that time, they can reflect the lightning from the sky. Okay, so for panchromatic, so-called pan, the image has a better the image have a better resolution, 2 meters. For multispectral, the image has a less spatial resolution, is 8 meters. But for spectral resolution, the panchromatic record the wavelengths from 5 to 0.8 micron. And multispectrals have 4 bands for the blue, green, red, and infrared. So the spatial resolution is the first we should mention. We should consider the resolution of a satellite. As you can see, the satellite spot 1 to 3, they have a spectral resolution pink. For pink image is 10 meter, a multispectral is 20 meter. For SPECT 4, the pink is 10 meters, multispectral is 10 meters. For spot 5, the pink image is a 5 meter, and the multispectral is sorry. For spot 5, the pink image is 10 meter, and multispectral is 5 meters, and the spot 5 also provides a super image, which is a fusion image, and provide the spatial resolution of 2.5 meters. And we have a spectral resolution and radiometric resolution. And here is a spot satellite and formal satellites list, and show the spot 1, 2, 4, 5, 6, and 7. And for formal sets, it's formal set 2 and 5. And we can take a look at the spatial resolution here from 10 for pink, 20 for multispectral. Right now, the spot 7 and 5 is a pink for 1.5 meters, and multispectral is 6 meters. For formal set 2, the pink has a resolution of 2 meters, and multispectral is 8 meter. For formal sets, the pink is 2. The multispectral is 4 meters. By the way, those image can be provided free for Taiwan National Science and Technology Council if you are eligible to submit a project. So if those students you want to use those satellite image, you can connect the scholars in Taiwan and collaborate with them. Then you can get a free satellite image. And we take a look at temporal resolution. That means revisiting time. For spot is 2.5 days. Spot 4 is 2.5 days. Spot 6 and 7 is 1 day. Formal set is 1 day. Formal set 5 is 2 days. 2 days. Spectral resolution, you can see pink and multispectrals. More bands have a higher spectral resolution. Okay, in this session, 3 points you should remember. One is imaging methods, including passive and active remote sensing, and 2 satellite system, geostationary and some synchronous. in which sun synchronous is suitable for Earth resource observation. And resolution capacity include spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. If you want to use satellite image to do your project, you should consider this full resolution before you choose one of the available satellite images. Okay, so this the take-home message. You should know what remote sensing is, why I need to learn remote sensing, how remote sensing technology work, and where I can get remote sensing data. Here I want to show you. Here I want to show you a case provided by NASA, how they use remote sensing to help them to map
The largest country in
the
Africa
future.
is in the heart of the continent. Known as the DRC, the Democratic Republic of the Congo suffered civil war between 1997 and 2003. Perhaps the only good thing to come of the civil wars are the country's vast, untouched forests, which weren't logged because war was bad for business. But what will happen to this vital resource now that stability is returning to the DRC? And how can local communities take ownership of this, their home, and secure a better future?
The DRC has not had any formal system of land tenure. I've been working with the African Wildlife Foundation, and we've been working with them to lend our spatial data expertise, remote sensing capabilities, analysis of satellite imagery, help them with their on-the-ground zoning activities, which they're formalizing with the government of the Democratic Republic of the Congo for land rights and for land use planning with local communities.
Spatial data expertise, remote sensing capabilities. What do these words mean exactly? For over 10 years, this satellite has been orbiting the Earth. It's called Landsat 7, and with every loop it takes around our planet, it collects information about the Earth's surface, which people like Janet can then interpret.
So we can feed information derived from Landsat imagery into a variety of models for land use planning in this landscape. And one way we've been using it is to identify the areas of highest conservation priority. So we've been working in the Marenga-Lapore-Wamba landscape, which I sometimes call MLW. It's in northern DRC. It's about the size of South Carolina. And it's full of tropical moist forests. So using Landsat imagery, we were able to zoom in on this particular forested area, connecting two protected areas in the east central part of MLW landscape. And it's an important corridor for the migration of bonobos between the protected areas, as well as other terrestrial species.
Once the AWF identified this critical area for conservation, it began working with the government and local communities on mapping the region. The mapping process has a dual benefit, preserving biodiversity and helping local villagers to secure their own land use rights.
Oui, carte ezali likanisi moko ya malamu. Po carte ezali makoma, ezali na papier. Bo atake bandelo ya lupango nanga ezali. Bana tango mususu bayebi esika lupango ebandi pe lupango esuki te. Me lukula sika wa grâce na zonage tango babimisi par exemple carte ya lupango oyo mwana akozala na facilité munene pona kuyeba esika lupango ebandi pe lupango esuki. Pe ekozala epa na ye docteur soki bato baye akolakisa bango facilement sans pour autant que alobaki tozalaka nde boye lopango na biso ebandaka nde boye lokola kaka ezali document monene oyo ekede ata na génération ya culture.
During the DRC war, humans hid in the forests to escape violent conflict. It was their refuge. And still now, the forest provides them with food, air, and shelter. With the help of Landsat imagery, this vital resource can be managed and preserved for the benefit of wildlife and generations to come.
Last year, there are several top technology trends we so-called ABCDEFG. A is AI, artificial intelligence. It's a very hot issue, especially after ChatGPT has been announced last December. And the second one is a blockchain. Then the third one is cloud computing. Cloud computing is relative to high performance computing. That's why TSMC Taiwan semiconductor company is so hot in Taiwan and in nationwide. D is a data cube. E is edge computing. I will talk a little bit about edge computing later on. And F fog computing and 5G or beyond 5G, and even in the future we will have 6G. For AI, I define AI is a composite of three major components. One is big data, and two is deep learning, and three is applications, is domain knowledge. Big data can be divided into two parts. One is labeled data, another one is unknown data. We use labeled data to train AI model so that they can identify unknown objects in the future using unknown data. And labeled or so-called training data is a very expensive. In mainland China, there are 1 million people working in this area to label the image to train different various AI models. For deep learning, we have algorithm and computing capacity. One is a software, another one is hardware. There are many major company or research centers are developing AI algorithm. And again, which used in ChatGPT is one of them to generate image or text automatically. And computing capacity gets higher and higher so that the computation become more efficient right now and even in the future. But most of them most of them are not our business. We only learn some algorithm or use some like NVIDIA GPU to run our program. But most of people can involve in AI area is because of their domain knowledge. The domain knowledge include various areas, including medical, finance, and manufacturing, agriculture, service, and education. So the lower part is our focus in the later on lecture. There are three AI steps. Right now, we are at weak AI. It's a specific AI, so-called supervised AI. So we train the AI model to do one specific purpose. So we should tell the AI model what is true, what is false. Then AI will recognize it and memorize it. Basically, AI model in AI model there are a lot of parameters. That's what we should determine at the first. So it only can do one thing, such as facial recognition or autonomous driving, or like AlphaGo can only do Go game. The next step is a strong AI. It's a general AI. It's a unsupervised AI. That means you don't have to train your AI model, then the AI model can train themselves. It's a AI model can provide a multi-functional and can reasoning like AlphaZero. You don't have to teach AlphaZero to how to play Go. They can learn by themselves, and even they can beat AlphaGo in the end. And general AI can be expected to have a motion expression, and that is a human be afraid of in the future. In the third step, we gonna have a super intelligent AI. The super AI is active, and uh, they can solve problem. They can think smarter than human. So several scientists think it's the end of the human world. So what we China develop is use AI is like left hand side. We use AI to develop a smart traffic or smart city, and as the famous film so-called Minority Report that grab uh, several forecasting people, then they can prevent crime crime occurrence. But this can be done by AI if you know what kind of a situation, like a temperature or how many people getting together, what kind of activity they have been doing, then some kind of criminal activity could happen, then you can prevent it in advance. So we like to have AI to help us to connect the vehicle automatically, especially for autonomous driving. And at that time, we don't have a traffic jam, no, at all time, and we can save a lot of effort for driving, for transportation. However, it could be taken over by some evil, like Fast and Furious 8. They showed if they can remotely control the autonomous cars, then it could be a disastrous. Okay, back to our remote sensing. We have different remote sensing image resources. Here is multi-sources image data, especially for smart agriculture. We have like 400 to 1,000 kilometer altitude that's satellite images, and we have 2,000 to 7,000 meters is an area image with a human pilot, and we have a little bit lower altitude UAV image. It could be a couple meters to a couple hundred meters. And we have close range images like your digital camera and the CCTV or any kind of device equipped by yourself. And different imaging can provide different functions. Like a satellite image can identify agriculture develop over a wide area. Like we can use satellite image to do crop investigation. How many area for rice? How many area for wheat or some other agricultural crops? For aerial image, we can identify the health of the crops. For UAV image, we can identify the health of crops even for every individual plant. It's never been done before because it's hard to observe every individual tree or plant on the ground. For those closer range image from your digital camera or your smartphone, they can help us to get some true data to train a AI model for remote sensing data. Remote sensing imaging has a different spatial resolution, as I mentioned earlier. Satellite image could be the resolution could be 2 meters, like on the photo on the right hand side. The area image has an altitude like 4 kilometers meters, 4,000 kilometers. I mean, the resolution is 0.2 meter or 20 centimeter. UAV can provide various spatial resolution to 10 centimeter to 1 centimeter, even less than 1 centimeter, depends on the camera resolution and the flying height. On 19 on 1997. Sorry, on 2019, there's a satellite image provided by Digital Globe for the oil field in Quake. The story is Iran sent a couple UAV to bomb those oil tank, so that at that time approximately 7 points of impacts on the key infrastructure is increase about 20% of oil stock market and make a very large damage about this oil supplier, but with very less cost, so that UAV becomes very important tool or equipped to do something good or bad. And in recent years, Russia war in Ukraine, we can see a lot of UAV playing a key role, especially for Russia or for Ukraine. They use a lot of different UAV to against each other to drop bomb or to damage the tank. So UAV becomes a very hard issue in Taiwan right now or in nationwide. We used to use a UAV to take 2D photos, but right now 2D photo is not enough. We want to establish a 3D model by the 2D photos. Like here we have a 2D planning or designing draw, and we hope we can have a 3D demo model. Right now, traditionally we use photogrammetry technology to establish 3D model using area photo, but those area photo are precise and accurate imaging in the sky, and they use a stereo pair to generate 3D model. Recent year, computer vision area develop so-called image-based modeling, IBM 3D construction. They need not so accurate photo to establish a 3D model. And this technology suitable for a main vehicle imaging system. So we can retrieve any video or some or a serial photos taken by others or in YouTube. Then you can generate a 3D model by those serial film. And after 3D model has been built, you can use Lumia to do some light effect so that you make it more true. And UAV can take a greater number of the photos, then generate the point cloud, which can be generated by LiDAR, but LiDAR is more expensive. So we use UAV image and we mentioned above the IBM technology to generate a point cloud and overlap with the image to generate 3D model. So this is a 3D model of our campus, National Zhongxin University. We built this model 10 years ago. And this model can be printed out by 3D printer, which what you see is a 3D printer's outcome. And we need precision agriculture right now than ever because in 2050 food production must be more effectively because we have a more population to feed, and we need a better farm efficiency. So we should introduce new technology in precision farming. And agricultural industry will need produce 70 more food, while only being able to use 5% more land. In precision agriculture, precision agriculture is a management strategy that gathers, process, and analyze temporal, spatial, and individual data, and combine it with other information to support management decision according to estimated variability for improved resource use, in efficiency, productivity, quality, profitability, and sustainability. So that means we need to do more sensing and do like as I mentioned, we need to do data collection, data analysis, and provide decision making reference. This is a example in Holland. A farmer use a Formoset 2. Formoset 2, as I mentioned, launched by Taiwan. It's a 5-meter in spatial resolution. They can identify the crop health, and then they can based on this outcome, they can decide their strategy of cultivation. Also, we can use UAV or drone to help to process precision agriculture. This is one of Taiwan UAV companies, so-called GeoSet. They can use UAV to collect UV, visible, NIR, IR images, and they can analyze those images and generate some vegetation index like NDVI, OSAVI, NDWI, and so on. So they can identify health spectral and yield spectral for the crop monitoring and health assessment. For the last 4 years, we have been researching on UAV application to crop cultivation support system. In this system, we have 3 major components. One is UAV agricultural image datasets. As I say, datasets is the essential component for AI. And the second task is UAV and UAV image analysis. So we established several different AI model to identify different objects like for crop health, crop loss, or yield prediction. And we also established a UAV cloud platform on agriculture, so we can exchange those UAV data, or it's convenient for the farmers to upload their UAV images that we can do image process for them, then and provide a cultivation support system for them. Here is some example, like we can use AI identification on crop growth. We send a UAV to get a high spatial resolution image, and also high spectral resolution, including RGB image, thermal image, or multispectral images. So we upload the UAV image to the cloud, and we train the AI deep learning model to predict the growth stage. And we also train the AI model to identify the pest and the disease. Like we apply this kind of technology to identify rice fever. And another one is AI yield and loss estimation use deep learning. We send a UAV, then get aerial photos upload to the cloud, then apply AI deep learning model to evaluate the loss due to natural disasters. We will give you an example later on. So for example, take rice for example, we can modify the AI model for rice growth monitoring from seedling stage to vegetation stage to maturation stage, and we can monitor the disaster damage and yield prediction. On the ground, we have some spectral correction board so that we can correct the noise from the atmospheres, and we can estimate the plant height from 3D models, and we can estimate the green cover rate for a paddy. When the crop mature, we can estimate the optimal time for harvest. For rice, take rice for example, we can traditionally we should take the rice to laboratory and test the moisture control for the rice. But right now we collect a lot of sample and train the AI model, so we can use a smartphone to take a photo. Then we will know the years, the rice year with a certain moisture contents, and predict when is the optimal timing for harvest. And we also train the AI model and equipped on a UAV, and the UAV can instantly identify the crop. For ground moisture detection, at first we have to collect label or so-called trending data. As I mentioned before, it's the most expensive stage in AI model establish. A proper grain moisture content assure the quality and quantity of the harvested crop. So how can we use UAV and smartphone to identify the grain moisture efficiently and over a wide area is the purpose of this project. And this is a non-destructive sampling, so we don't have to take the crop from the plant. So it's efficient, very efficiently, and because it's very cheap to sample each point, so we can do it over a very wide area, have a lot of data, and coupled with weather prediction, then we can predict when is the optimal timing for harvest. For rice damage, we use UAV to identify rice lodging, because rice lodging is a major loss for rice. Rice lodging costs annually loss of $1 billion, and almost one third paddies occurs rice lodging every year. So we traditionally they should when rice lodging occurs, they should send experts to the ground on site, investigate the damage of the rice lodging. But because the damage area is so huge, more than 1,000 or 10,000 hectares at one disaster's event, so it's impossible to collect data for each paddy. So we developed a flight UAV flight route and take photos. Back to the laboratory, we mosaic those photo and do AI identification to discover where and how much percent for paddy for the disaster relief, because the government has a rule said if paddy has can get a disaster relief only if the damage is more than 20%, but it's hard to identify on the ground. But it's easy for the UAV images. So we have a pilot study over 300 hectare rice paddy. We fly the UAV at flying height at 220 meters, get the spatial resolution of almost 5 centimeters. And on the ground, we deploy several control points, and then we get a 3D model like this. The color represent the altitude of the plant. So the red area means those area has rice lodging, and then we can level with cadastral map, so we can know the damage percentage for each paddy, and know who can get a disaster relief from the government, and we also reduce the field survey from 1 month to 1 week. So it's a very big progress for damage assessment.
Important is to organization you have to virtual disaster. First, we detect rice paddy using time series satellite images, such as Sentinel-2. Once heavy rains and storm strike, unmanned area vehicles will immediately sent to an updated area image with the rice object identification. In addition to the spectral information in digital service model and texture information will also add image-based anomaly and texture analysis. All those may be eligible for disaster relief.
Okay, due to the time limit, if you want to see more details for this research, please refer to this paper, Remote Sensing, published in remote sensing, spatial and spectral hybrid image classification for rise lodging assessment through UAV image. And UAV image can the rise lodging could occur over a very wide area. So if you want to do a very precise assessment, it's very expensive. So we develop with use an AI model to do rise lodging identification. We use a SecNet, FSCN, AlexNet. We separate a mosaic photo into many tiles, then send them each tile to the parallel computers to do rise lodging area identification. Then the mosaic then again to get a damage map. Of course, we should change the AI models. Then we should do the model test. And because we use parallel computing, so we can save a lot of time from 2 hours to 4 minutes for 80 hectares. This has also been published in the Remote Sensing journal. It's a highly cited paper. So if you are interested, you can get this paper for your reference. Due to time limitation, I have to skip this all this information because UAV provide very precise spatial resolution, so we can identify each single plant and monitor each single plant during the growth stage. Okay. We also do some oyster farm monitoring before and after typhoon to estimate the damages. Due to time limitation, right now I want to skip to this. Remote sensing is a new technology. They can coupled with other technology like drone, smartphone, robots, and Internet of Things, so-called IoT, and use AI and machine learning algorithm to analyze those remote sensing data. So in the future, it's our dream to integrate satellite data, IoT sensors, drone, and GPS and autonomous vehicle to do our smart farming, and we can use a very less human power to do a very wide area and controlled by the computer. In the future, we're gonna have a 5G and edge computer research on this area. If you want to, I will skip this. So on the UAV, we will equip the AI model and the edge computer. So when we spread a chemical for the pesticide, we can monitor the health of the crop first, then adjust the concentration of the chemical. So we can save a chemical and can prevent the residual of the chemicals for environmental friendly purpose. Okay. We also try to use a UAV to monitor the solar panel and the turbine. and we use the same technology on the smart land to monitor the smart city. So finally, the take-home message will be what AI remote sensing can benefit us. So you can think about it, and how AI remote sensing can be applied. So what kind of technology you should learn before you apply AI model, and why I need to learn AI remote sensing, and where I can uh, learn AI remote sensing more. So if you want to know more about AI remote sensing, you can email me. This is my email address, so you can email me if you have any interest or question, or you can visit our website, so you can get more detail about what we are doing. Maybe you are interested in our labs, and I hope you can get in touch with us in the future. Okay, it's all my lecture. Thank you very much. Back to you.
Thank you, Professor Yang. And Meng-Der, do you have something to announcement? Oh, sorry, here is some question, right? Yeah, Professor Yang, can you see the question in the chat room,
Okay,
in the chat box?
Okay, let me check the chat box. May I ask the NIR map is passively detecting that the three wavelengths of NIR red green, and then integrate the results on one map at the same time, and then observing different information such as plant health. Yeah, what you mentioned is correct. So you can integrate NIR red green together on one map, and you can also process those image, then generate a new image like VI, vegetation index map, so that you can reflect the health of a crop on the ground. And we also can identify the location of each single plant, and you can provide the reference for different cultivation strategy. So that's right. It's in one map. Okay. If you have any question, you can send me an email. I will glad to reply you. Another question is, I would like to know, how did you detect the UAV drug spraying distribution? Okay. As I mentioned, if your UAV equipped with edge computers, and the edge computers has a trained AI model, so the AI model can identify the health of the crop and decide the a, a, a suitable concentration of the fertilizer or pesticides. That's how we adjust the spraying concentration. There's a question about many people are worried about the stage of the super AI. If robots are combined, they may surpass the human control and even threaten human survival. Can Professor Yang offer your thoughts? Yeah, I think it's possible, but it could. I think it can be prevent before it come true, because right now, along with the technology development, a lot of ethic and law regulation has been developed at the same time. So I think they are a lot of regulation will come out and to prevent the disaster in the future. I hope so. I cannot make so sure 100%, but I hope so. Thank you for your question. There's a question: does it use NDVI or some index sales? More and more edge computing applied in the world. Yeah, NDVI a lot. Besides NDVI, there are many other vegetation index you can use. It depends on what kind of situation you wanna identify or you wanna observe, like soil moisture or the temperature of the crop. They are different sensors can be equipped on UAV. So the device should be the design and the flying height should be designed at the first, depending on what kind of purpose you are pursuing. Okay, thank you very much.
Okay, let's thank Professor Yang again. And please
Okay.
that Ming-Der has something to announce. Thank you, Professor Yang.
Okay. Thank you very much.
Thank you, Professor Yang and Dr. Xu. Okay. Anyone please write down this Google Form, and if you have more questions for Professor Yang, you can also write down in this Google Form. We'll pass your question to Professor Yang.
Okay. Bye-bye.
Bye-bye.
See you.
Thank you.